In this chapter, we will look at shapes and drag coefficients, cross sections of spokes, be they round, rectangular, oval, or elliptical, and then fluid flowing through a constriction, pressure and velocity thereof, fluid flowing around a streamlined object, pressure and velocity, fluid flowing around an arrow spoke, pressure and velocity, and then aerodynamic drag of spokes, be they round, rectangular, oval, or elliptical. Spokes come in all sorts of dimensions. My choice varies with intentions. We'll view oval and round and what options abound and try to reduce apprehension. The extent to which various shapes can contribute to aerodynamic drag can be expressed as mathematical coefficients. Drag coefficients are dimensionless numbers that allow us to compare the aerodynamic profiles of different shapes, so a lower drag coefficient is better and will offer less resistance and less drag than a shape with a higher drag coefficient. This is a table that shows drag coefficients, three-dimensional on the left and two-dimensional on the right. If we look at the three-dimensional side, we see a couple of examples. Here we have a hollow half sphere, and it is slanted away from the oncoming air, has a drag coefficient of 0.38. On the other hand, if I turn that around so it becomes more like a scoop, then I have a much higher drag coefficient because clearly there is more drag. On the two-dimensional side, which we are really primarily concerned about, here is a circular cylinder, the onrushing air, and we have a drag coefficient of 1.17. Down here, a square cylinder with a picture of the air coming toward it, and a drag coefficient of 2.05. And going back up to the top, our circle then can be viewed as a cylinder, and the square as a square cylinder. Now let's look at our rider riding into the wind, and we're going to focus on this one spoke here and consider three different shapes that spoke might have. Either a rectangular cylinder, or a circular cylinder, or more of an oval cylinder. And we're going to look at all three of these and compare them, but I want to call the spoke at the top a brand X bladed spoke because it's obviously different in its shape from the oval spoke at the bottom. Let's compare the brand X bladed spoke to a round spoke. And for the sake of comparison, we're going to make them have the same cross-sectional area. Brand X bladed spoke has a cross-sectional area of 1.98 square millimeters. For the round spoke to also have a cross-sectional area of 1.98 square millimeters, it's going to have a radius of 0.794 millimeters. I've taken the time to draw these to scale for you pretty well, so these representations that you see pictorially here are pretty good. That would give me a diameter of 1.59 millimeters. We'll just call that 1.6. And there are many wheels out there that have spokes in them that have a diameter of about 1.6 millimeters. I'm back to showing the radius of the round spoke, and we're going to take the bladed spoke and rotate it 90 degrees. Then we have this picture. But I want to see this in three dimensions. In three dimensions, I would see a picture like this, and I'm going to look at these two spokes from this perspective. Then I had this picture, and you might think of this as what the air sees. If these spokes are in a wheel and they are rotating forward towards the oncoming air, this is what the air has to get around. These two spokes, as you're looking at them, are rotating toward you. Let's make the length of these spokes 280 millimeters. As the bladed spoke rotates towards us, toward the oncoming wind, we see the dimensions there, and we have a frontal area of 252 square millimeters. The round spoke, with dimensions as shown as it rotates towards us, toward the oncoming air, presents an area of 445 square millimeters. But we can't assume that the ability of the air to get around these two shapes is the same. On the right, where we have a round cylinder, the air is meeting a curved shape. On the left spoke, with a rectangular cylinder, the air is meeting a flat shape with sharp corners. These are the two relevant drag coefficients we saw a minute ago: circular cylinder at the top and square or rectangular cylinder at the bottom. We put in those drag coefficients from the table. When I multiply those out, I get what's called the CDA, which is 5.17 times 10 to the minus fourth square meters for the bladed spoke, and 5.21 times 10 to the minus fourth square meters for the round spoke. You can think of it this way: the round spoke, even though it presents almost twice the frontal area to the onrushing air, because of its lower drag coefficient, the ability of the air to get around the thinner bladed spoke compared to the wider round spoke is about the same. Remember, in these pictures here, we're looking at the frontal area of these spokes, and the frontal area of the bladed spoke is less than the round spoke. But they have the same cross-sectional area, which means if they both have the same length, they will have the same volume of stainless steel in them and therefore have the same mass. Which means with the bladed spoke as shown here, even with a smaller frontal area, it may not result in a faster wheel than the round spoke. Let's make a little table of what we have so far. Drag coefficient on the frontal area times the frontal area gives me the CDA, the product of the two. So our table is going to list for different spokes the CD, the frontal area, and the product of the two in square meters. For a round spoke, we found that we got this. For the rectangular bladed spoke, we found that we got this. Now we want to turn to our Supreme C X-ray spoke, and let's say that it has the same frontal area as the rectangular bladed spoke, but I want to know what the drag coefficient is on this and then be able to estimate the CDA. My Supreme C X-ray spoke looks very much like that oval spoke shown at the bottom, and I want to examine its aerodynamic drag characteristics. Now we're going to look at some graphics that depict how fluids can flow around streamlined objects. Bernoulli's principle describes the relationship between internal fluid pressure and fluid velocity. It's actually an application of the law of conservation of energy, which states that energy cannot be created or destroyed. Using this section of garden hose as an example, there's a term called the mass flow rate, and that is equal to the mass of the flow divided by the unit cross-sectional area, and that is constant at all points in the hose, which means that as the diameter of the hose goes down, the fluid speed must go up. As we already know, total pressure is equal to dynamic pressure plus static pressure, and that will be constant at all points along the hose, which means that as the dynamic pressure increases, the static pressure must decrease. The blue line represents the rate of flow of water, which is slower in the wider sections of hose, faster in the middle section, and slower down here again. And as the rate of flow increases, the static pressure has to decrease, and we can see the static pressure as indicated by these red lines. This is the well-known Venturi effect that tells us that the static pressure will go down as the speed of the fluid increases through a constricted area. But the total pressure remains the same because in that same restricted area, the dynamic pressure, which is pushing the fluid longitudinally through the constricted area, increases. Let's look at a graphic that shows in better detail how the rate of flow changes inside the hose. On the left in Station 1, we see lines representing the flow rate of various layers of water, all of which are traveling at the same speed. As these two lines enter the more restricted area, their speed increases slightly. As we move away from the center, we see that these two lines, getting closer to the side of the hose, are increasing in speed more than the first two did. That same trend continues in these next two layers, even more speed. At every point on the very inside surface of the hose, as indicated by these blue lines, is what's called the boundary layer. The boundary layer is extremely thin, but the force of attraction of the hose to the water molecules immediately next to the side of the hose is so strong that the boundary layer is actually stationary. And that accounts for why we see in this outermost line here that the water doesn't accelerate as much as we might have expected it to, because it's immediately next to the stationary boundary layer. So this very first layer here is slowed by friction with the boundary layer. Other than that, the outermost lines of water are moving the fastest through Station 2, the restricted area. A little slower here, and a little slower here. Using this picture here of water flowing through the hose, if we imagine that we can take the top of the hose off, then we would see this picture here, only looking at the water flow through the bottom half of the hose. The curvature of the restricted part of the hose is still going to cause water molecules to pile up, trying to get around that restriction, and that will cause the pressure to increase, and that will accelerate the flow rate of the water. Here's the same picture, except this time it's air. We'll cut off the top half of the hose, trim off the ends, and then look at the diagram of the air moving through the hose in the bottom half. It looks just the same as the other diagram did. Air molecules pile up, and that causes an increase in pressure, and that accelerates the layers of air shown in blue lines. But as I get farther from the edge of the hose, I start seeing upper layers of air that are flowing more or less unrestricted, and the blue lines are sandwiched in between the curvature of the hose and those upper layers of air. What we have actually depicted is the upper half of an airfoil. And it would be a symmetrical airfoil, as we see at the bottom. The other kind is a non-symmetrical airfoil, shown at the top. This is a wing, which we're in a position to now understand quite well. This yellow line here divides the wing into an upper camber and a lower camber. In the upper camber, we have a greater flow rate, greater dynamic pressure, and a lesser static pressure. In the lower camber, we have the opposite, a lesser flow rate, lesser dynamic pressure, greater static pressure. The greater static pressure in the lower camber is only partially offset by the static pressure from the upper camber, and the balance is what gives the wing lift.